Hello student, welcome to the web optics course. Today we have lecture number 61 and we will going to continue with the way we polarize the light. So, today we have lecture number 61. So, in the last class we discussed how we can polarize the light by reflection. So, let me do it once again because that will be useful to understand how we can polarize the light by scattering. So, polarization of light by reflection. We have already discussed this, let me do it once again. So, when we calculated the Brewster law, so that was the incident light having polarized light like this, and that was the transmitted light where the electric field vibration was this. So, when the electric field vibration was this in this direction, then it will vibrate the molecule in this direction and it going to radiate this. So, there will be a, so these are the dipoles basically, and it will suppose it is vibrating in this direction. So, if it is vibrating this direction, it will radiate along this direction, along this direction, along this direction, but the amplitude of this thing will depend on the theta. If it is along this direction, then what happened? So, if I write this is a theta, then when sin theta is equal to 0, that means along this axis of dipole no scattering will be there. There will be no, not scattering, no radiation. So, here the dipole is vibrating this direction, and if I write this is my theta, then it is radiating along this direction. So, I will going to get a component in this direction which is perpendicular to which is like this. Now, if I try to understand what is this theta in terms of initial angle, suppose this is my I. So, this angle will be I, then say this is my R, and this total angle is 90 degree because this line. So, this total angle from here to here it is 90 degree. So, I can write, so what is this angle? So, let me define this angle, yellow line. If I write it as x for example, so x plus I plus R, that has to be angle pi, that is a pi, right. And this angle x and this is theta and it is 90 degree. So, x plus, because these two lines, this dotted line and this red line and this dotted line, this dotted line and this line, they are parallel to each other. So, x plus this angle which is pi by 2 minus theta should be pi as well. So, what I have is I plus r from these two, I plus r will be equal to pi by 2 minus theta, that I get. Now, what happened if theta equal to 0? If theta equal to 0, that means that is the direction. So, when theta is 0, then the dipole that is vibrating along this will not going to radiate any radiation along this side. So, that is the condition one can achieve when I plus r is pi by 2. That is a very special condition, and that special condition we derived in the last class. So, let me draw it. So, here I have this radiation with this polarization, and when it enters it have this vibration, but here because this angle is 90 degree, whatever the radiation it generate because of the vibration of the dipole, so this component will not be there. So, whatever the radiation will have in the reflected ray will be only this component, and that is polarized. Now, if this is N1 and N2, we calculated that this incident angle should be such that tan of I will be N2 minus N1. In order to have I plus R equal to pi by 2, this condition need to be there. So, this is R and this is I. So, that condition we achieve only to make theta equal to 0 such that no radiation is there. So, that we discussed in the earlier class. So, today we will going to discuss that using this how we make the polarized light by scattering. So, a similar concept will be there. So, today we are going to discuss polarization by scattering. So, what happened in the scattering? Let me draw it once again. When the electric field is coming, which has a frequency say omega, and it falls on a system where we have dipoles, and these dipoles will start vibrating. So, there is a vibration of the dipole, it will vibrate, and we know that when the dipole vibrates it start radiate. So, radiation will come out from this dipole vibration, and this is scattering field. This scattering field E will be proportional to P double dot, that we need to know. And what is P? P is dipole moment. Now, P is charge E multiplied by the distance r during the electric field when there is a dipole, then there is a separation of the charge. So, this separation is r. So, if I write P double dot, so it should be essentially E r double dot. That means it is proportional to acceleration. Now, r double dot is proportional to omega square. How I get? Because if electric field, if I define this as r cos omega t, sorry, E naught cos omega t, then r, which is a function of time, will be also represented in this Lorentz model. If I do r 0 cos omega t. So, r double dot will be simply omega square is proportional to omega square. From here we can get. So, P is proportional to the scattering power actually. Scattering power big P is proportional to the electric field square, and that should be proportional to omega to the power 4. So, P is essentially, scattering power is essentially proportional to omega to the power 4 or 1 by lambda to the power 4, and that is our well known Rayleigh scattering. So, what happened that this power, whatever the power we have, scattering power, will be proportional to 1 by lambda square. So, if lambda is small, then the scattering power will be high. So, for lower lambda we have higher scattering. Now, what happened in, so what happened that when the light is falling to some system, and this is a unpolarized light, suppose it is falling, and it will be, this polarization will allow the molecule to vibrate along this direction and this direction. So, this is unpolarized light. So, what happened if I look from a certain direction which is perpendicular to that, then we can see only one polarization that will come from this vibrating molecule. Why? We will going to explain. We have already explained that in the previous calculation. So, this will be polarized or partially polarized. One can quickly understand this by considering, suppose this is a sun emitting radiations and here we have our earth, surrounded by atmosphere like this, and this is our earth. So, the radiation that is coming from the sun actually comes here and it is unpolarized. So, both the component will be there, and let me draw this component. Like this. So, when it interacts with the atmosphere, what happened that suppose we have a molecule here and this molecule will vibrate either this direction, it will vibrate, this is one way it can vibrate, this is the molecule that is vibrating, maybe I can put a different color to make these things. So, this is the molecule, it will vibrating in this way. Or it can vibrate, in this way, I mean perpendicular to this. So, I just let me erase this. So, it will vibrate perpendicular to the direction. So, this is the direction I am talking about, in this way, perpendicular to the page of the paper. So, when the molecule is vibrating in this way, it will not going to radiate anything here. So, no radiation. Because dipole, if I draw quickly, that if this is a dipole, if it vibrates in this side, no radiation will be there. The maximum radiation will be perpendicular to this radiation. And no radiation. So, no radiation will be here. On the other hand, when it is vibrating perpendicular to this, then there is no point, there is no problem, we can have radiation for this vibration. So, from here what we see is the light that is scattered from this and come to earth will no longer have this component, only this component will be there. Same thing happened in the opposite, when the light fall in the opposite direction, and when I look the thing from here, we will see that only these components will be there, even though there were unpolarized light that is coming from the sun, but only this. So, these light are partially polarized. So, this is the way when we have a scattering, then there is a possibility that we get a polarized light. This is one way to polarize the light. This is sun and this is earth, E. So, now let us go forward and see that what happened for other cases. I mean, what are the other way? So, another way to polarize the light is by birefringence. I listed that in the earlier class. So, polarization by birefringence. So, it happens for optical anisotropic crystal. The optical properties are not same in this kind of crystal. So, optically anisotropic crystal is such that anisotropic crystal are such optical system or optical material for which the optical properties are not same. In all direction. That is, I can draw a schematic figure that I have a electron cloud and I have a spring mass system like this, considering that electron are vibrating under the presence of electric field, but the vibration of the electron is different in different directions. So, suppose this is one direction, this is another direction, and this is another direction. Suppose this is my x direction, this is y direction and this is z direction. So, schematically we represent the binding force of the electron cloud in a different direction, and like a spring with different spring constant, the vibration of this electron cloud is no longer same in all the direction when in the subject to the application of an electric field. So, that system can leads to an anisotropy because the property is not same in all the direction. So, that basically leads to the optical anisotropy. In very simple way, I just try to explain without going to a detailed analysis of how it works and all these things, which is not required at this stage because that is not our topic. I just try to make you understand that how this optical anisotropy arises in optical system, and simply this anisotropy arises because of the different optical property in different directions. That is the way. A simple example of this system because of this. So, the direct consequence is that, so because the binding force is different. So, the refractive index is different in different direction. So, whatever the value we have for a, suppose we have a crystal here like this, and if I assume the axis like this, x, y and z. So, if I move along x direction, if I move along y direction, and if I move along z direction, the refractive index may not be same, and that is the main feature of an anisotropic crystal. And this kind of crystal is essentially called the birefringent type of crystal, or in general this property is called the birefringence. This is called the birefringence. So, in case of birefringence, what happened if I draw the refractive index profile? So, this refractive index profile for x and y will be different. For example, if I draw a refractive index profile for with respect to omega, and then this is the way the refractive index is plotted. It goes up and then there is absorption and it goes down. So, the point where it goes down is called the absorption band. So, suppose this is absorption band, and this is suppose this is ny, the refractive index along y direction. If I plot the same thing for a birefringent crystal, one can see that maybe this value is different, and one can get refractive index profile where the absorption being shifted to some place in x. So, the point is, with respect to omega, if I plot nx and ny, they no longer coincide. For isotropic system they coincide, but for anisotropic system they no longer coincide. So, for this kind of systems, what happened, that means in two direction we have two kind of refractive index. We get a property that if I launch a light, so in one case the refractive index will have the electric field will see one refractive index, and in another direction the refractive index will going to see the light will going to see another refractive index. So, the propagation of the two component of the light will no longer same, because the refractive index is different in two different directions. We do not have much time to discuss more about how this birefringence should work. In the next class, however, what we do, that we will discuss this more to assuming a specific crystal which exhibit this kind of birefringence, and try to analyze how the electric field, when the electric field is propagating this system, how the different component of the electric field will experience different refractive index or different velocity. And we know that when the two different component, two perpendicular component rather, experience two different velocity, so there will be a phase lag between these two components, and when there is a phase lag, so whatever the light you launch and whatever the light you receive, they may not be in the same polarized mode. So, that means utilizing this crystal, we change the polarization, maybe from linear polarized we get circularly polarized or different kind of polarization. So, that means we produce some specific polarized light by exploiting this kind of material, where by using the refractive index different we basically use the phase relation, we differ the phase relationship between x and y component and get the result. So, with that note I would like to conclude here. Thank you very much. See you in the next class.